Dr. M.A. Bhagaveni, Professor, Department of Electronics and Communication Engineering, College of Engineering Gindi, Anna University, Chennai. Dr. M.A. Bhagaveni graduated from Government College of Technology, Coimbatore, has completed her Masters and PhD at College of Engineering Gindi, Anna University. Her field of interest includes cognitive radio, ad hoc networks, wireless sensor networks, and wireless communication. She has completed two projects, one for CVRDE and the other for DST. She is the recipient of Young Scientist Award from DST. She has got two Best Research Paper awards in international conferences. She has published more than 70 research papers in reputable journals and conferences. She is author of two books. The one is Analog and Digital Communication and the other is Cognitive Radio, an Enabler of Internet of Things.
Welcome to the UGC lecture series for BSc Honours. This session will be covering frequency modulation transmitter and receiver experiment. The aim of the experiment is to transmit voice signals using frequency modulated transmitter and a receiver. The apparatus required to do this experiment is the FM transmitter kit, the FM receiver kit, the connecting probes, the cathode ray oscilloscope or the digital storage oscilloscopes, microphone and a speaker. Theory: in this we will just see what are all the signals that can be passed using your FM transmitter. Generally we say audio frequency. What is called as audio frequency is nothing but the acoustic, mechanical or electrical frequency corresponding to the normally audible sound waves, which are in the frequency range approximately 13 to 13,000 kilohertz. So, these are the audio frequencies. This will be the source signals which we will be using to transmit using the FM transmitter. Usually we have radio frequencies generally classified as very low frequency, which will be 3 kilohertz to 30 kilohertz, low frequency 30 kilohertz to 300 kilohertz, medium frequency 300 to 3 megahertz, high frequency will range from 3 megahertz to 30 megahertz, very high frequency ranges from 30 megahertz to 300 megahertz, ultra high frequency ranges from 300 megahertz to 3 gigahertz. Now, all these frequency ranges are generally called as radio frequencies. Audio frequencies are between, we have seen as 13 hertz to 13 kilohertz. What we are going to transmit is an audio signal will be converted to a radio frequency signal by the FM modulation kit, power amplified and then transmitted using an FM transmitter. So, these are the frequency ranges that are generally used to transmit the signal in the radio range. It is the general electromagnetic spectrum, where we can see we have the various frequency ranges. Generally these are radio and TV waves, which will range from 10 power 4 hertz to 10 power 8 hertz. After that we have microwaves, followed by infrared light, ultraviolet, X-rays and gamma rays. Out of these set, all these are used for general communication. So, radio waves, TV waves, microwaves, all are used in microwave communication. So, in general all these frequencies there is this communication going on. Lesser than your radio waves will be having your audio waves, which will be generated by the source. We are going to use the same frequencies as it is generated by the source, we cannot transmit over a larger distances. In order to transmit the signal over larger distances, we modulate the signal, convert it from the baseband frequency to a higher carrier frequency and then transmit it to reach a farther away distances. For doing this, what we require the most is the oscillator. It is called as local oscillator. The oscillator is the heart of a transmitter. It creates the frequency that the transmitter emits. You can fix the oscillator using crystal oscillator or a variable frequency oscillators. So, there are many methods or ways to create an oscillator. Once you have the oscillator, this oscillator will act as the carrier generator, which will generate the frequencies of transmission. A simple block diagram of any transmitter will include a oscillator, a buffer to store the oscillated signals, power amplify those signals and pass it using an antenna. All the blocks are circuits. So, they are empowered or provided power using a power supply block. In the place of oscillator, we can have either AM modulated signals or FM modulated signal. This is a simple transmitter block diagram. You need to have a signal, you need to power amplify the signal and transmit using the antenna. A continuous wave transmitter has the following blocks. We will be having a master oscillator, a driver buffer, a power amplifier and an antenna. So, you will be transmitting the telegraphic keys. These telegraphic keys will be the key to select the particular oscillation frequency and power amplify the signal and pass it using the antenna. Like this only we are going to build up now a common FM transmitter. Fundamentals of frequency modulation includes the frequency modulation changes the frequency of the oscillator with respect to the amplitude of the message signal. Here the modulated wave will have the amplitude the same as that of the carrier wave, but the frequency of the signal will change with respect to the amplitude of the message signal. Like in AM transmitter, we will be having a modulator stage in the FM transmitter, which will be using the oscillator to modulate the message signal or the audio frequency signals. FM will have the best local communication because the audio signal will be very hi-fi and you can easily understand even when the signal is very weak. This is because the signal is mostly used for line of sight, very high frequency or ultra high frequency, and also that the message is not carried over the amplitude of the carrier signal, as the amplitudes are worst affected by the noise in the channel. Now, in FM, the message is carried over the frequency changes of the carrier, which is not affected by the noise. So, the audio what you get out of an FM communication will be of very hi-fi or high means it is of very good quality. These are general equations that are corresponding to a frequency modulation, where we will be having the instantaneous change in the omega will be equal to whatever might be the carrier omega plus gain of the VCO times amplitude of the message signal, gain of the VCO times the amplitude of the message signal. So, once the omega instantaneous value is changing, the phase of the signal will change, which will be nothing but omega t of t plus the gain of the VCO times integral m of t dt plus C phi. This m of t is the message amplitude. This will make the phase change continuously. This will make the FM modulated signal to change its phase continuously. So, AC cos omega t plus phi of t, which will be nothing but Cf integral m of t dt. So, as you can see over this diagram, we will be having as the input voltage changes, this is the voltage axis, as the input voltage changes, the frequency that is being given at output will also change. If you are going to give this as the input voltage, you get a frequency output which value is equal to this point. If you are going to give this as your input voltage, the frequency that you obtain will be this value. So, that is how the VCO will help to change the input voltage, that is changes in the amplitude to that of changes in the frequency. This is the basic concept that is used in FM modulation. A typical FM modulated waveform for a single carrier will look like this. We will be having a signal and a carrier wave. Once it get FM modulated, you will not be having any amplitude changes. This is an example of amplitude modulation, where the message is imbibed over the peaks of the carrier signal, but in FM the signal will be imbibed over the frequency changes of the carrier signal. It will be looking like this. FM modulated signal will be looking like this. There will be a group of signals bunched together, group of signals that are sparse apart, right. So, that depends upon the amplitude of the input message signal. So, whenever the group of signals are bunched together, you have a higher amplitude. When they are sparse apart, you will be having a lower amplitude message signal. So, this is how a typical FM modulated waveform you can look in. But as an FM transmitter which is going to modulate not just a single frequency, it is going to use audio frequencies. Audio we have seen already 3 to 13 kilohertz ranges. So, it is a band of frequencies, every frequency is going to get modulated like this. So, we will not be able to exactly see how the FM modulation is. Only thing what you can note is the amplitude will be constant, there will be no change in the amplitude at all, whereas the frequencies are either bunched together or spaced apart. You have your message signal as we see in the oscilloscope. This is a FM typical transmitter diagram. We have to take a kit, to the kit we have to connect a microphone. Microphone will get at the input from the human beings which are within the audio range. We speak through the microphone, that speech signal is amplified using the speech amplifier, then they are frequency modulated using FM modulator. To the FM modulator, we have the input called as oscillator, then the signals are power amplified and it is transmitted using the antenna. So, this is a typical FM transmitter diagram, a microphone, a modulator, an amplifier and an antenna. This is a typical FM receiver diagram. We can receive the signals using the antenna. The received signals are in the radio frequency range and they are amplified using a radio frequency amplifier, which are enough to trigger the circuits that are available in the mixers. So, up to that level they will be amplified and they will be given as input to the mixer. The mixer will take an input from the local oscillator. Combining these two will be converting the radio frequency signal to the intermediate frequency band. This process is called as heterodyning, where the higher frequency signals are down converted to intermediate frequency bands. So, the mixer will produce frequencies between Fc plus Fm and Fc minus Fm, where Fc is the carrier frequency that is obtained from the oscillator, Fm is the message signal that is obtained from the antenna. It will produce Fc plus Fm and Fc minus Fms and they are filtered to get only the low frequency component, that is your Fc minus Fm part. So, that region is called as intermediate frequency and those intermediate frequencies are amplified using IF amplifiers. Then these are passed through a limiter. The purpose of the limiter is to limit any amplitude variations in the IF amplified signal. So, if at all there are any amplitude changes due to the noise level, they are removed by the limiter circuit. As they are removed, we will be passing it to a FM discriminator. Discriminator is nothing but a frequency to voltage converter. You can use the popular Foster-Seeley frequency discriminator, where we will be using balanced modulators to convert the frequency modulations, the amplitude modulations in the FM signal to voltage changes. So, after frequency discriminator, your IF signals are converted to baseband signals and these baseband signals are audio frequency amplified and they are going to drive the speaker. So, this is the set of blocks that are involved to receive the FM signal. So, RF amplifier, a mixer, a filter, IF amplifier, a limiter, then the frequency demodulator, then comes your audio frequency amplifier and we will be going to drive a loudspeaker. So, these are the available in the kit. Now, we will see how the procedure to operate the kit and see how FM transmission happens. The procedure is to first switch on the trainer kit and check the power supply, connect the microphones at the point marked mic in the trainer kit. To transmit audio signals, we have to talk through the mic. So, we are the source who generate the audio signals. The audio signals are FM modulated, power amplified and transmitted by the antenna. The transmitted signals can be viewed using just viewing at the test points named aerial. So, using DSO, now we are going to see what type of signal that is being transmitted from the FM transmitter. Then to at the receiver end, switch on the receiver trainer kit and check the power supply, connect the speaker at the point marked on the trainer. With the help of the tuner, tune the circuit to the required frequency. We need to tune the circuit to the frequency that is transmitted by the FM transmitter. So, we have seen in the last class that it has transmitted around a megahertz range frequency. Now, you need to vary the tuner to see that the same frequency, the tuner will exactly map on to the point of regenerating same the transmitting frequency at the receiver end. Once the tuner maps on to that of the transmitting frequency, we can hear whatever we have talked in the speaker. So, as we tune the FM tuner, we may come across many direct FM channels that are transmitted as FM radios. In between, we can even hear those radio signals from a live FM receiver. So, then we need to observe the voltages and waveforms provided at the test points. So, this how you do the FM transmission and reception using real voice data that has been transmitted using the transmitter and received using the receiver, heard using the speaker. There are few characteristics of the radio receivers. Generally, we talk about what is the selectivity, sensitivity, stability, image rejection as general characteristics of a receiver. Selectivity, as the term implies, it is a measure of the ability to separate received signals. We have seen at the receiver end, there are many radio signals which will be emitted by many real time devices, like it may be other FM which will be operating in the same frequency what we are using. There will be other microwave devices, TV signals are available, AM signals are available, all those signals will be there already available in the air. From the air, what is the capability of the receiver to pick up our required signal? That is called as selectivity. This usually is measured in terms of Q of the tuned circuit. Q of the tuned circuit. As you vary the tuner, what you do actually is you are going to change the center frequencies of various channels. As if you pick up the center frequency of one particular channel and the channel is of bandwidth 10 kilohertz, you should have a short cutoff filter which will pick up only plus from the center carrier frequency plus 5k this side and plus 5k that side. If the slope is not so smooth, then it will pick up adjacent channels also, and you can hear only a noisy signal at the receiver end. So, selectivity is it's one of the important parameter where you are going to see that whether the receiver is having the capability to pick up the required signal. Then you have another parameter called sensitivity. Sensitivity is the measure of the receiver's ability to detect weak signal. So, as the signals are moving over the air, there are many clutters available in the environment. So, because of this, the possibility that the signal will be corrupted by noise is very high. So, if your receiver is very sensitive, it can even pick up the weakest signal that is available in that particular frequency. If your sensitivity is very poor, even the strong signal cannot be picked up by the receiver. So, you can measure what is the sensitivity of the receiver. It is nothing but the ratio of signal to noise power that can be intelligibly heard from the receiver. That is called sensitivity of the receiver. Then you have another parameter called stability. Stability is a resistance to frequency drift caused by the temperature, voltage variations and proximity to the body, because the receiver is built up using many discrete components. When you continuously try to use it, we may feel the temperature of the devices or the ice is becoming very high. So, because of the change in the temperature created of the continued use, the frequencies that are generated may also change. So, this may create instability in the receiver. So, to avoid instability of how stable is your receiver even after many continued changes in the voltage, continuous changes in the variations of the input voltage and proximity to other bodies. For all these things, it should be immune to changes. So, usually they are measured in terms of parts per million. Another concept called as bandwidth describes how wide the filter is in the front end of the radio. The bandwidth must match the bandwidth of the desired signal. For example, for continuous wave, the bandwidth of the signal is about 500 hertz, whereas for FM it is 10 kilohertz, which will be centered at the center carrier frequency with plus or minus 5 kilohertz. This is for armature FM. For normal radio FM, it occupies nearly 20 kilohertz, center carrier frequency plus 10k this side and 10k that side, plus 10k and minus plus or minus 10 kilohertz at the center. So, this is what a bandwidth means. We should design the filters in order to pick up exactly the required bandwidth. If we design a filter which is having a very low slew rate, it will pick up adjacent channel signals also. So, from this, the audio signals are transmitted using FM transmitter and received using FM receiver. That is the results of this. Finally, in summary, we have to turn on the transmitter kit, give input as voice signals through the mic. These signals will be FM modulated, power amplified and transmitted through the aerial. We can just see what frequency the signals are being transmitted. As it FM modulated, we can exactly see the frequency changes in the DSO, how the frequency varies from one center carrier frequency to many frequencies, because it is not a one single tone what we are going to modulate and transmit. It is a band of signals that are generated from the human voice, which will be ranging from 3 to 3 kilohertz. So, all these frequencies will be FM modulated. We can't exactly say this is the range of frequency or that will after modulation. So, therefore, we can see a group of signals at the aerial point with some voltage assigned to those signals. So, then to receive these signals, you need to turn on the receiver kit, connect the speaker, tune the tuner to receive the particular frequency what we have transmitted. So, within the range of the frequency changes, we are able to tune the speaker, we can receive whatever we have talked. So, by this we have transmitted our speech and received our speech at the receiver end. Questions? What will happen if the sensitivity of the receiver is very poor? You can also think of what will happen if the selectivity of the receiver is very poor. Name few applications where frequency modulation is used for transmission. Last question, what are the advantages of frequency modulation over AM modulation? Thank you all.